All right, so we're going to talk about work and energy and power today. One of the longer units we do. Definition certainly has a different definition than regular work does. It's based on a formula. Work equals force times distance. The formula gets modified later on with a little bit of trig. So work is done when an applied force causes an object to move some distance. Sometimes you hear them say displacement instead of distance. Sometimes that's a better way to think about it if you understand displacement. And this also has to do with the motion of the object. Now, if you think about the formula, you go with F equals F times D. Excuse me. If you go with work equals force times distance, well, obviously, if there's no distance, then no work is done. This guy here, trying to lift these weights, is exerting a force on the barbell, but the barbell's not moving any, which means D would be 0. So by physics definitions, he's not doing any work. No work is being done by the weightlifter. The units for work are the joule. Sometimes you'll see a Newton meter, and that's pretty easy to see that. If work is in Newton meters, then you know that newtons is for force, and displacement or distance is in meters. So that's a unit for work, a Newton meter. But sometimes you will see it as a capital J, which stands for joules. And James Joule is an inventor of the steam engine. Interesting little factoid there you don't need to know. But Newton meters is the unit, and joules is the unit as well. Very important concept. Work is done only when components of a force are parallel to the displacement. Let's take a closer look at that. We have a box that is being pulled at an upward angle. We don't know what theta is, but we know that it's being pulled at an upward angle. So we have components. We have the component that we call the x component, and we have the component that we call the y component. And when this box is moving to the right, we know that by definition, the only part of the force being applied that can count is the part of the force that's moving parallel to the motion of the box. And if the box is moving to the right, it's moving this direction, then this part, this x component, would be the only part of the force we could count, which is why sometimes you will see it written work equals force times distance cosine theta. Now, you could do force cosine theta distance. It doesn't really matter what order you put them in since they're all multiplied together. Of course, sometimes the force is perpendicular to the movement, like a waiter carrying a tray across a room. The waiter's pushing, or waitress is pushing up on the platter, but the platter's moving in a horizontal direction. So in that case, we'd have an angle of 90 degrees, and of course the cosine of 90 is 0. But sometimes it's in the same direction, like if I lift a book up into the air and pushing up on the book is moving up. Force and distance are the same direction. So the angle between the force and the distance is 0 degrees, and the cosine of 0 is 1, which means really, in that case, you don't even need to plug it in. Now, sometimes there's such a thing as negative work, where the angle of the force is directly opposite the displacement, like holding a book and letting it go directly downward. You're pushing up on the book, but the book is moving in a downward direction, so you'd have the force of the book going up, and then the displacement would be down. And if the displacement and the force angle is 180, well, the cosine of 180 is -1, so you'd have negative work being done. We'll get into that later. Speaking of that, positive or negative work. Let's take a look. When your force and your displacement are in the same direction, then you have positive work being done. So if you're pushing your friend on a sled, here's the sled, and you're pushing to the right, here's the ground, right? You're pushing to the right. Well, the sled's moving to the right, the displacement's to the right, and the applied force is to the right. So the angle between those two is 0 degrees. And of course that would give us a +1. But there's also work being done on the sled by friction. So if we just focus on friction, it would be what? It would be kinetic friction in this case. You have the objects moving displaced to the right, but friction's working to the left. Well, this angle is 180 degrees, and the cosine of 180 is -1. So that would give you a negative answer if you were trying to solve for the work. So anytime you have a situation where the force is one direction and the displacement is opposite that, that's negative work. But when you have force in one direction and displacement is in the same direction, that's positive work. So speeding up, the overall net work would be positive, and slowing down, the overall net work would be negative. We know that when we talked about forces that it was the net force. If something had a net force, that way we knew the object was accelerating. If it didn't have a net force, if the net force was 0, we knew that the object was not accelerating. So if an object isn't accelerating, it can't have a net force. Therefore, if an object is not accelerating, this is very important, then the net work on it is 0. It doesn't mean there's not work being done on an object. If I'm pushing a sled and I'm pushing at a constant velocity, I'm doing work on the sled. Friction's doing work on the sled, but the net work is 0 because the net force is 0. Why is the net force 0? Because if I'm pushing a sled at constant velocity, the sled is not accelerating. And again, if you don't have acceleration, you don't have net force. And if you don't have net force, you can't have net work. So anytime the net force is 0, then the net work has to be 0. Again, doesn't mean there's no work being done. It just means the overall net work is 0. Oh, I haven't mentioned this, but work is a scalar quantity. Work is a scalar quantity, and it helps when you're doing work to just look at the magnitudes of the force and the displacement. And if the answer is negative, the negative will come out when you do the angle. The cosine of 180, for example, will give you a negative answer. So here we have a car that is moving along at a constant speed. And of course, constant speed should mean to you that we have 0 net force. And if we have 0 net force, we have 0 net work. We know the engine is doing 200 newtons of work to the right. We know friction is doing negative 200 newtons of work to the left. Therefore, there is work being done. If I wanted to figure out the work done by the engine, I could take the force of the engine multiplied by the displacement of the car. But overall, the net work on the car is zero. If I wanted to find the work done by friction, I would take the force of friction on the car and multiply it by the displacement of the car. In both cases, I'm going to get a value. Here I'm going to get a negative value. Here I'm going to get a positive value. But those would just be values for work done by the specific force, like work done by friction and work done by the engine. If you combine the two, where the net force is zero, well, if the net force is zero and you put a zero there, well, that just cancels everything out and you don't have any work done. Now here we have a situation where the engine's putting out 300 newtons of force and friction is only putting out negative 200. Well, if that's the case, what would be the net work done? Well, if you have 300 going one way and you have 200 going the other way, that means that the net force on the car would be 100 newtons. Now we have a situation where, since the net force is 100, we would have a value for net work other than zero. We would plug in 100 right here, and whatever the displacement of the car was, we'd multiply that, and that would give us our net work. So we'd have positive net work here because the object's speeding up, right? We talked about that earlier. Now here we have a case where you have 200 newtons from the engine, you have 300 newtons from the friction force, you end up with negative 100 for your value. But even if you didn't have the negative sign in there, you know that the angle between the force on the car, which would be overall this way, and the displacement of the car, which would be that way, that's 180 degrees. And you know the cosine of 180 degrees is negative 1. So that's going to give you a negative value for your answer for net work anyway. You should be able to look at that and see, though, that because the negative 300 is more magnitude-wise than the positive 200, that you're going to have a negative answer. So this would have negative net work on it. And you can tell, again, because the car's speed is getting less, it's decreasing. All right, so we have a tugboat pulling a ship with a horizontal force of 5,000 newtons. It's causing the ship to move through the harbor. How much work is done? So they want us to find the work done by the tugboat on the ship if it moves a distance of 3,000 meters. All right, so this is just about as basic as you can get. We know work equals the force times the distance. I'm going to go ahead and put cosine theta here. And we know the force is 5,000. We know the distance or displacement is 3,000 meters. And we know that when we multiply those together, we get 15 million. Now what about this cosine? Well, if the ship is moving, let's say to the right, with certain force of the engine, and the displacement is in the same direction, what's the angle between the force and the displacement? Well, it's 0 degrees, and the cosine of 0 degrees is 1. So we really don't even need that part of the equation in this problem. And what would the unit be? Well, it would be joules, or you could put Newton meters. That's perfectly acceptable. The friction force from the air and the water is equal to 2,500. How much is work done by friction over the same distance? Well, remember now, if the force of friction is 2,500, and it's the same distance, right? It's the same distance of 3,000. Then the work done by friction is going to be the force of friction times the distance times cosine theta. So the force of friction is 2,500. The distance is 3,000 meters. And that would be cosine of what? Well, it would be cosine of 180 degrees. Because if the ship is moving to the right, so the force is to the right, and friction, sorry, if the ship is moving to the right, so the displacement is to the right, and the force of friction is opposite that, what is the angle between those two arrows? Well, it's 180 degrees. So the cosine of 180 is -1. So we would get a negative answer for this one, and it would be 7,500,000. And what would the unit be? The unit would be joules, or Newton meters if you wanted to put that. So there's our answer for the second one. To this question here. So if we wanted to find the net work, we would want to find the net force first. Well, if the force of the, again, let's draw a little free body diagram here. Here's the ship. If the force of the engine of the ship is 5,000 newtons, and then there's a friction force of 2,500 the other direction. Well, if it's 5,000 one way and 2,500 the other way, how would you get the total net force? Well, it would be 5,000 minus 2,500, which is 2,500. So the net force times the distance. Well, it's the same distance, right? 3,000. And then the net force is now 2,500. So the net work is going to be 2,500 times 3,000, which is 7,500,000. So that would be the net work, 7,500,000 joules. And that's the net work, right? You could have also just taken this number, the 15 million, and subtracted this number, 7,500,000, and you would have gotten the same answer in both cases. So there's really two ways to do that one. Let's go back. All right. A shopper at Kroger pushes a cart with a force of 35 newtons, directed at an angle downward 25 degrees from the horizontal. Find the work done by the shopper, and that's going to be in joules, as the shopper moves along a 50-meter aisle. So that would be the distance. All right, it might help to draw out a free body diagram for this one. You know that we have our FW. You know that we have our normal force. We know that this is being pushed at that sort of angle. We also know that that would have components. this would be our, this is applied. So this would be FAY, and this would be FAX. And this value is 25 degrees. And then we have friction pointing the opposite direction of the motion. And that would be kinetic friction. And we're supposed to solve for the work being done. Well, we know that the work done by the shopper is equal to the force of the shopper times the distance that the cart moves. And for this one, because there's an angle given, I'm going to put cosine theta. Now remember, the rule with work is that the only force that counts is the force that's parallel or anti-parallel, meaning pointing the other direction. The only force that counts is the one that's parallel to the motion. Well, the cart's moving to the right. So which one of these components is pointing to the right? Well, that would be FAX. And we know FAX is a adjacent side to the 25 degrees. And we know that SOHCAHTOA tells us cosine is the adjacent and the hypotenuse. Adjacent over the hypotenuse. So we know we're going to plug in our 25 degrees here to give us our work done by the shopper. So the force of the shopper, 35 newtons, times, might be easier to put the cosine after the 35 since you're used to that from when we started doing dynamics originally. We always put the hypotenuse and then we put the trig function right after it. So cosine of 25 times the distance of 50 meters. So when we do that, we do 25 cosine, 35 cosine 25 times 50, we get 1,600 joules, or 1,586 joules. I guess we could round that, 2 sig figs to 1,600 joules. So that would be our answer. The second part of the question says, is this the net work done on the cart? Well, have we accounted for friction at all in our answer? No, we drew it in the picture, but we didn't account for it. We would have to know how much friction was going the other way so we could find the net force, and then from that we could find the net work being done. So this is not the net work. This is just the work being done by the shopper. The second one, down here at the bottom, if 2 joules of work, so it's giving us a work value, 2 joules of work is done by raising a 180 gram apple, okay? 180 grams, that's a mass, and I also know that that's 0.180 kilograms, right? Just divide that by 1,000. And I also know that FW equals mg, and in this case m is 0.180, mg is of course 9.8. So the weight, I'm not really worried about the negative versus positive here. That's why I didn't put the negative sign in front of the g value. So our weight is 1.764 newtons. That's how much the apple weighs, is 1.764 newtons. And they want us to figure out how far. So they want us to find distance. And that'd be in meters. So if we know if work done is equal to the force times the distance, and I'm not even going to worry about the cosine of theta here, because if I'm doing work raising an apple, I'm lifting it up in the same direction that I'm applying my force, so I don't need to worry about the cosine of theta, because it's going to be 0 degrees between my force that I'm applying to the apple and the displacement of the apple. So cosine of 0 is 1. So I can just ignore that. But in this case, I have to do a little bit of rearrangement. So the work equals the force times the distance. The distance equals the work divided by the force. Well, the work done was 2 joules. I'm going to put Newton meters instead, just to show you where the unit comes from, divided by the force required to lift the apple up. Well, it would be the weight of the apple. I mean, if I'm trying to lift something up and it weighs 1.764, then that's how much I have to apply to lift it up at a constant velocity. And we see that the newtons cancel. And so 2 divided by 1.764 gives us 1.1, and then of course meters is the unit. So power is the rate at which you do your work. Working overtime, that's a good mnemonic device to remember it, although you don't have to remember it because you get to use your formula sheet all the time. But if you take the work done and you divide it by the time that the work is done, then you get power. And you could write it FD instead of T. And if you think about it, you know that distance over time is equal to velocity. Well, what do we see right here? What do we see in this spot? We see distance over time. So power actually can also be solved by doing the force times the velocity. So there's a couple of ways to solve for power. There's an example of what I just said. You see your d over t right there. Change to v. Now, watt is the unit for power, and that wasn't a question, that was a statement. Watt is the unit for power. Watt is W-A-T-T. James Watt invented the steam engine. I think I may have said that James Joule invented the steam engine earlier, but I was wrong. It was James Watt that invented the steam engine. My apologies to James Watt for claiming it was James Joule that invented it. But the unit for watt, the symbol for watt is a W. And what's the symbol for work? Well, the symbol for work is a W. So when one of these is a unit, like it's something that you would put after a number, and this is simply a variable, a measurement. So this is something you would see in a formula, and this is something you would see as an answer to a question, a math question. So sometimes I'll write watts out. Sometimes I'll just put joules per second, and that saves me a lot of trouble. Just be careful here. It's very easy to get the two confused. Now, watt should sound familiar. Yes, it is the same watts that you use when you talk about electricity. Kilowatt is something you hear more than watts when it comes to electricity. A kilowatt is equal to 1,000 watts. And when you get billed by your power company, they base it on the cost per kilowatt hour, which varies from state to state. And we'll talk more about that when we get into our electricity unit. Hopefully you get my joke here. This is a 1 horsepower engine for that car. I always like that joke. 1 horsepower car. But a horsepower is more of an American or English unit. It's not technically a metric unit, but there is a conversion between horsepower and watts, and that's 746 watts is equal to 1 horsepower. So if you ever need to convert between watts and horsepower, there's your number that you need. You're either dividing or multiplying by 746, depending on what you're trying to convert. And of course, many engines are sold with the idea of their whatever their horsepower is. But that could be, you could sell it in watts as well, but horsepower is just more common. All right, so we have an electric motor providing 500 newtons of force. So our force is 500 newtons over a distance of 10 meters. Our distance is 10 meters. And this happens for 2 seconds. Our time is 2 seconds. And the question says, what is the power output of the engine? So we want to find the power output of the engine, and that's going to be in watts. Well, we know that power equals work over distance, work over time, work over time. And we also know that work equals the force times the distance over time. So this looks like just a plug and chug problem here. Our force is 500 newtons. Our distance is 10 meters. And this all happens in a span of 2 seconds. So what is our power value? Our power output is 2,500 watts, or joules per second if you would want to write joules per second. So there's our power for that first one. Number 2, how long does it take a car's combustion engine rated at 134,000 watts? That right there sounds like a power value. And that's 180 horsepower, in case you were wondering. To do 300,000 joules of work, well, we know work equals 300,000 joules. And we're trying to find time. Well, we know that power equals work over time. And if we were going to rearrange this, we know that T, time, equals work over power. So time equals the work done, 300,000 joules, over 134,000 watts. And of course we know a joule per second is also a watt. So we could really, instead of writing watts right here, we could write joules per second. And that way we can see that the joules end up canceling, and seconds is our leftover unit, which makes sense because we're trying to find time. And you get 2.24 seconds for the time. Now let's separate this out here. We'll try and do all of our work for number 3 above it. A 1,700 kilogram muscle car. So the mass is 1,700. With a wide open throttle, can accelerate at 5 meters per second squared. The muscle car travels 160 meters, so distance is 160 meters, in 8 seconds, so time is 8 seconds. And friction is equal to 1,000 newtons, so the friction force is 1,000 newtons. And the question says, what is the net force of the car, and what is the power output of the engine? So again, what is the net force of the car, and what is the power output of the engine, and then what is the net power applied to the car? I know you can't see it on the screen. If you have your notes handout in class, though, it's legible. The software appears to have cut it off when I imported the slide. But I'll take you through it as we're doing it. It might help to draw out a free body diagram here. So let's do that off here. We have the car. We have the car. And I'm just going to draw the left and the right forces here. I'm not going to leave off the normal force and the weight. We don't know the applied force of the engine. All right, we don't know what that is, but let's just say it's moving to the right. We know the friction force, and I'm going to draw that here, and that's friction is 1,000 newtons. So I know the friction force is 1,000 newtons. We know the weight of the car. We don't really need that. But they do give us some information that's going to help us with A. So how would we solve for part A? What are we going to do for part A? Well, the second law says that the net force of any object is equal to the mass of that object times the acceleration of the object. Do I know the mass? Do I know the acceleration? Yeah, I know both of those. I know the mass is 1,700, and I know the acceleration is 5. So really, I just have to plug them in and multiply them. So 1,700 kilograms times 5 meters per second squared. And that's going to give me a net force of 8,500 newtons. So that's your answer to A right there. This is answer A. So I can come over here and say, okay, my net force is 8,500. Of course, we don't really include a vector in a free body diagram for net force, but it's going to help us later on to solve for B. All right, so let's think about it. If we're doing B now. If I know the value that I want to find, and it says in B, I want to find the power output of just the engine, then I need to know the work done by the engine divided by the time. Well, the work done is the work done by the engine divided by the time. That's also the same thing as the force of the engine times the distance it's moving over the time. How do I find the force of the engine? Well, let's think about this. I'm going to have to go way up here to do it. If the force of the engine equals the net force plus the friction force, then I can plug in those two values. Now you might be wondering, well, how in the world do we know that the net force plus the friction force equals the force of the engine? Well, I could rearrange this and say, well, the net force, isn't the net force the difference? And when we say difference, don't we mean subtraction? If the applied force is pushing one way and the friction force is pushing the other way, the net force is the difference between those two. In other words, it would be the force of the engine minus the friction force. So all I've done is I've taken this and I've rearranged it into this. So how in the world do we find force of the engine. Well, do we know the net force? Yeah, we found it. It's 8,500. It's 8,500. Do we know the friction force? Yeah, it was given to us. It's 1,000. So what's 8,500 plus 1,000? Well, that's 9,500. So that right there is the force of the engine. It's like if you were trying to figure out the force of the engine when there was no friction. That's what we're saying when we want to know the force of the engine. If you could just look at the force going to the right, the force applied, how much was that? So we're going to plug in for force of the engine 9,500. Distance we know is 160 meters. And the time is 8 seconds. So we plug in 9,500 times 160 divided by 8, and we end up with 190,000 watts. So that is our answer for the power output of the engine. And then for C, we'll try and fit C over here. For C, they want us to find what is the net power output. Well, what's the net power going to be? Well, it's going to be the work done, net work done, divided by the time. And the net work is going to be the net force times the distance over the time. Well, what's the net work? What's the net force? Well, the net force is 8,500. That's what I saw for in A. 8,500 times the distance. The distance is still 160 meters. That's not changing. And the time is still 8 seconds. So what's the power output net? Well, what's 8,500 times 160 divided by 8? That's 170,000 watts. And there's your answer for C. So now we're going to transition to energy. And energy and work go hand in hand. That's why we do them together. There's an idea called the work-energy theorem, which says that the work done is equal to the change in the energy. And believe it or not, the energy and work, same unit. They're both in joules, so they have everything in common. Well, we know there are lots of different types of energies. The definition of energy, the ability of an object to do work, is kind of a generic definition, but it is exactly what you would see in any textbook, regardless of whether it's a physics textbook or a chemistry textbook. So the ability of an object to do work. There are all kinds of energies. There's thermal energy, there's chemical energy, there's electrical, there's mechanical, there's nuclear, there's electromagnetic, there's magnetic. There are all kinds of things. And you study these various types of energies as you go through your career in science education. We focus in this unit over mechanical energies. We focus on this one right here. We may incorporate some of the other ideas listed here, but for the most part we just talk about mechanical energy when we're talking about energy in this unit of physics. So what is mechanical energy? It's energy due to the position of an object or the movement of an object. Position and movement. And there's two basic types. There's potential energy and there's kinetic energy. Potential energy is stored energy. Um, when you have potential energy in something, it has the ability to do work. So gravitational potential energy is the one you're probably most familiar with. And gravitational potential energy, you could use, say, this is a picture of Starr's Mill, and years ago, of course, we had a wheel that was connected to I believe it was grain, but it grinded the grain. There's a little tube that went in here and then grinded it. But as the water would come over the mill, it would push this wheel. So we were taking the water's potential energy and we were using it to turn this wheel. And as the wheel turned, the shaft turned, and the shaft was connected to things that grinded up grain down to tiny bits, and you could use it for whatever you needed to. If you take a hammer and you raise it above a nail, you are giving it energy as you raise it up. And of course, the fun one is a roller coaster car at the top of a track. There's a lot of energy stored in this car way up here, and that's about to be released as it goes down the hill. Now, gravitational potential energy is not the only type of potential energy. There's also elastic potential energy. And elastic potential energy is energy you would get from something like a rubber band or a spring or a bungee cord, anything that stretches, an arrow, a bow, an arrow string. So there, you can have potential energy stored in more than just things that are high up. You can also have it stored in things that are stretched or compressed, for that matter. So the formula for gravitational potential energy is mgh, where m represents the mass of the object, and that would be in kilograms. G is 9.81 meters per second, but I don't mind you using 10 here. You can use 10 now. You've graduated to 10 meters per second squared. You can still use 9.81 if you want to, but that's not required anymore. And then h, of course, is the height of the object in meters. Now you have to have that based on a reference point. For example, if I have an object on a table, let's just say it's a box sitting on a table or a weight or whatever. If I call this the reference point, the ground, then the height would be here to here. But what if I label the table my reference point? Well, then it's sitting on that reference point, so the height would be 0. So it depends on what you want to do with the reference point. When you're doing a problem, you just have to be consistent. But usually the ground level is called the reference point, or the 0 line, some people say. But it's up to you. You just have to read the problem and use it as you see fit. But mgh, you just have to multiply those together, and that gives you the potential energy for an object. While we're on it, the elastic potential energy formula is 1/2 k, k being what we call the spring constant. And that would be something that it would be in Newton per meter, times x squared. And x is how far away the spring or the rubber band is from resting position. If you just take a rubber band and you just hold it without stretching it, that's resting position. And then if you start to stretch it, you're pulling it away from resting position. So x is what we call the resting position, and it would be that you'd square that value, multiply by the spring constant, and then divide by 2, and that would give you the elastic potential energy. But both of these are considered stored energy. All right, so let's say you're riding Daredevil at Six Flags, and it's got a 32-meter drop. Looks like that would be our H, 32 meters. Calculate the potential energy. So they want us to find the potential energy. We know that's going to be in joules. We have a 75 kilogram rider at the top. So the mass is 75 kilograms. And we have to find it at the top, at the halfway point, and at the bottom. Well, at the top, we know PE equals mgh. And we know M is 75. We know G is 10. And we know H is 32 meters. So we just multiply those together. That's it. We multiply them together. And we get 24,000 joules. And that's at the top. And then one of the things you have to understand with potential energy is it's very easy to convert when you're talking about halfway, midway, and at the bottom. If we're saying the bottom is, and this is at the top, but at the bottom, and again, if we're at the bottom, then the reference point is the ground, and that means that our value for height would be 0. So you should realize that at the bottom, it's going to have 0 joules of potential energy because it's lost all of its height. All of that has been converted into what we call kinetic energy at the bottom. And then at the midway point, well, at the midway point, it's lost half of its potential energy. So what's half of 24,000? Well, half of 24,000 is 12,000. And if you wanted to make it a math question, you would just take half of 32, multiply that by 75, multiply that by 10, and you get your 12,000. But you can reason it out without doing much math there. All right, our other type of mechanical energy is kinetic energy. And we see from our picture here that our formula has been cut off a little bit. So covered up here is mv squared. So kinetic energy is 1/2 mv squared. And that's the energy of motion. So you'll notice that it is definitely speed dependent because the v is squared here. Mass has a lot to do with it as well, but since we're squaring the velocity, it increases the kinetic energy exponentially. And this is one of the things you can learn about when you're driving. It takes a lot more to stop when you're going 60 miles per hour than when you're going 30 miles per hour. It takes a whole lot more energy to stop a car that's moving at 60 instead of 30. So the question says to find the kinetic energy of a 75 kilogram downhill skier. So we know mass is 75 kilograms. Moving at 40 meters per second. So the velocity is 40 meters per second. And we're being asked to find KE. We know it's going to be in joules. So kinetic energy equals mv squared, 1/2 mv squared, 1/2 m, 75, and 40 meters per second is our v, and that's squared. Don't forget to do that. So when we take our kinetic energy we have 75 for our mass, we have 40 for our velocity. Our kinetic energy ends up being 60,000, and the unit would be joules. Then we have another one, calculate the velocity. So we're trying to find V of 1,230 kilogram Ferrari, 1,230 kilogram Ferrari, with 500 joules of kinetic energy. So they're giving us the kinetic energy. So we know KE equals 1/2 mv squared. And if we were going to rearrange to solve for V, we'd multiply both sides by 2. We get 2KE. We divide by m. And then to get rid of the square, of course, we would take the square root. So the square root is 2 times our 500,000 joules over our mass of 1,230 kilograms. And our velocity would be 28.5 meters per second. Now, I mentioned earlier this whole work energy theorem, and the idea is that whenever you're doing work, whether that's lifting a book or pushing a wagon or whatever, that you're changing the energy. Okay. So if I wanted to raise something up from the first shelf to the top shelf, from the bottom shelf to the top shelf, I am going to have to do work on that book or object or whatever it is to get it from the bottom shelf to the top shelf. Because I'm doing that, because I am doing work to get that done, I am changing the energy of the object. In this case, I'm changing the potential energy of the object. So if I want to change kinetic energy of a car, for instance, if a car is moving and I want to stop it, I have to do work to stop it. And this will probably be the force of friction, right, more than anything to stop it. If it's not moving and I want to get it moving, if I want to give it kinetic energy, then I have to do work on it. So it's not a complicated idea. Mathematically, sometimes it can throw you for a little bit of a loop, but it's not that bad conceptually. So if I want to increase a car's speed, the engine does the work. If I want to slow a car down, the brakes do the work. In both cases, I change the energy. So we end up with, a big mess down here. Let me rewrite this for you so it makes more sense. And of course, you can look on your handouts to see. But if the net work is equal to the change in kinetic energy, then the net work is equal to the final kinetic energy, whatever that is, minus the initial kinetic energy. So if I have an object that's not moving, and then all of a sudden it has 10 joules of kinetic energy, the net work done on that car is 10 joules, or object, whatever it is. And we know that the formula for kinetic energy is 1/2 mv squared. But if it's the final kinetic energy, then it would be whatever the final velocity is, minus the same formula, right? The formula doesn't change. The 1/2 mv squared. But the initial kinetic energy would be the initial velocity. In both cases, the mass don't change. So this is really what is the work kinetic energy theorem. So all this down here, I've translated up here. And if you look in your notes, it's not screwed up like it is on this slide. And if we take it even further, and again, this would be F net times the distance, and this would be the change in kinetic energy here. And then change in kinetic energy would go right here. And of course we know that work is equal to the net force times the distance. So this down here, this big huge formula is what we call the work energy theorem. So there are many things you can do with this formula. You can see there's a lot of variables, but it's not that complicated. It's work here, change in energy here. It's the same exact thing we were talking about on the previous slide. So we have a student wearing some Bauer rollerblades, and they're pushing a friend with a constant force of 45. So the force is 45 newtons. And the question says how far, well that sounds like a distance, we know it's going to be in meters, must the student be pushed starting from rest? You should realize starting from rest means that the initial kinetic energy is what? Well, if kinetic energy is 1/2 mv squared and the initial velocity is 0, what's the kinetic energy? It's got to be 0. So that her final KE is 352. Joules. Well, if we write out our work energy theorem, we know that FD equals 1/2 mvf squared minus 1/2 mvi squared. Well, what's this value right here already? That's the initial kinetic energy. Well, that's this right here. So that takes that out of the equation. Do we have to do any calculations to get 1/2 mvf squared? Isn't that what the 352 is right here? So this would be 352 on this side. And then what's the net force? Well, the only force they give us was 45. That's all we have to work with. And distance is unknown. So how am I going to find distance? Divide both sides by 45. So it's going to be 352 divided by 45 newtons. And that gives us 7.8 meters. Remember, a joule is a newton meter. So if you divide a newton meter by a newton, your newtons cancel, and that's where you get the meters. So 7.8 meters is our answer there. All right, we have a train car with a mass of 200 kilograms. It's traveling at 20 meters per second. That's the initial velocity. How much force must the brakes exert? How much force must the brakes exert to stop the train? So you should be thinking, oh, stopping the train means that its final velocity is 0 in a distance of 10 meters. Well, let's think about our work kinetic energy theorem. We know that FD equals 1/2 mv squared minus 1/2 mv squared. Of course, the only difference here is the initial and final. What is the final kinetic energy? Well, that's going to be 0. F net is unknown. How far is this train going to be sliding? 10 meters. And do we know enough information to solve for the initial kinetic energy? You know the mass of the train, car, is 200 kilograms. we know the initial velocity is 20 meters per second. We're going to be squaring that. So we end up with 10 times F net equals, this gives you negative 40,000 when you multiply it all out. And how are we going to solve for F net? We divide both sides by 10, and we get a negative 4,000 newtons for our answer. Now, why is it negative? Well, the train is moving to the right, and that net force has got to be to the left because it's the only way it's going to slow it down, and that's in the negative direction. So there's your negative 4,000 newtons for your answer. All right, I think all of you have heard of the law of conservation of energy. It basically means that if you have one type of energy and you think that energy has disappeared, it really has not. It has simply just turned into another type of energy. If you have a car going down a track, it's got a lot of kinetic energy, and it all of a sudden comes to a stop. We say, oh, the kinetic energy is gone, but is the energy really disappearing? No, it's been absorbed and transferred into another type of energy, which would be heat, right? Because to stop the car, you got to provide friction, and that friction produces a lot of heat energy. So there's just an ebb and flow of energy changing from one type to the other. A pendulum swinging is a great example of this, and that's what the YouTube link is on the slide here, but I don't have it set up to go to it. We'll talk about it in class though, but I imagine that the URL is still correct. If you want to type that in and look at it yourself, you can. So here's what I mean. I mean, if you gas up your car engine, you know that there's plenty of chemical potential energy in the gasoline, and once you start to burn the gasoline, that gasoline energy through a chemical process gets converted into mechanical energy that's used to make your car go. And of course, not all of that energy that's produced by the engine goes into moving your car. There's a lot of wasted energy, heat energy that's produced that makes your car less efficient because of that high loss of energy that doesn't go into moving the car, that goes into heat energy and whatnot. So here's our formula for the conservation of mechanical energy. Now you'll notice that it starts out just putting initial and final on both sides, and as we go through it, we know that whatever the initial mechanical energy is, again, we know mechanical energy can be either potential or kinetic. So whatever the potential energy is at the beginning, plus whatever the kinetic energy is at the beginning, should equal the potential energy at the end plus the kinetic energy at the end. Okay. Well, what's the formula for potential energy? MGH. So this is MGH initial. KE, what's the formula for KE? 1/2 mv squared. So this is 1/2 mv squared initial. PEF, that's potential energy final. What's the formula for potential energy? MGH final. And what's the formula for kinetic energy? That really should be a capital E. 1/2 mv squared final. So this entire formula here is the law of conservation of mechanical energy formula. And it can come in quite handy when we're doing problems. Speaking of a problem, let's take a look. We say we have a ball that's thrown up into the air. How high will the ball go? How high will the ball go? So HF, what's the final height if it has an initial velocity of 12 meters per second? So we're throwing it up in the air at 12 meters per second. Now, let's write this one out. Remember, we have our initial potential energy would be MGHI plus our initial kinetic energy would be 1/2 mvi squared equals the final potential energy. The final potential energy would be mgh final plus the final potential energy, or kinetic energy. And that would be 1/2 mv squared final. Well, let's think about this. When I first throw the ball up into the air, the initial velocity is going to be given as 12, right? What will the final velocity be of that ball if it gets to its max height? How fast will it be going when it reaches its max height? Well, won't its final velocity be 0? And if that's the case, what can we do with this side of the equation? Well, if VF is 0, we can say bye-bye to that. How about over here on the left? When I throw the ball into the air, what is my 0 line? What is my resting position? What is my initial position, my height? Wouldn't that be where I'm letting it go from my hand? So wouldn't the initial height be 0? So what would happen to this guy here? It goes away. Now we're left with 1/2 mvi squared equals mghf. Well, algebraically, if you have mass on both sides and they're of the same object, is there anything we can do with those two masses? We can cancel them. We can get rid of them. So now, look what we have. We have 1/2 vi squared equals GHF. And what am I trying to find? I'm trying to find HF. So that would be equal to vi squared over, now how would I get rid of the g? I can divide both sides by g, right? So 2g. So vi, what is that? It's 12 meters per second squared over 2 times 10. Remember, you've graduated to using 10 for your g value. And we get a height of 7.2 meters. Now, could this problem have been done using kinematics? Well, what do we have available to us? We have the initial velocity of 12. We have g of 10. We have a VF of 0. And we're trying to find delta y. So does that qualify us for our 3 variables? It does. And we don't have time, so we'd have to use the 4th formula. We're solving for delta y, right? So delta y equals VF squared minus VI squared divided by 2g. So that would be 0 minus 12 squared over 2 times 10. And that's 144 divided by 20. And when you divide 144 by 20, you end up with 7.2 meters. So, which way did you think was easier? I think that this way was easier, but you could have solved for it a different way if you wanted to. So this is just a graphic showing us our conversion from potential to kinetic energy. We're trying to put this pylon into the ground. So we raise up our big mass here of some unknown mass, and we let it go. And as it falls, it gets faster and faster, so V is increasing, which means our kinetic energy is increasing, and our Potential energy would be decreasing because the height's getting less and less. And finally, when it hits the ground, all that energy gets released and pushes the pylon into the ground. We lose some of that energy to sound energy because, of course, if you've ever seen pylons for a bridge being hammered into the ground, you can certainly hear the sound of the pylon hitting the jackhammer trying to push it into the ground. This is kind of just of a pendulum idea. If the pendulum here is swinging back and forth, pendulum's moving back and forth. As we raise it up, it increases its potential energy because height is increasing. And then when we let it go, what's happening when we let it go? It's getting faster. So what's happening to the kinetic energy as it's getting towards this point? Well, it's going up. What's happening to the potential energy? It's getting less. Why is the potential energy getting less? Because it's getting less height. And then it moves up a little bit. So what's happening to the potential energy as it moves up? Well, its height's increasing. So its potential energy is increasing. What's happening to its velocity? Its velocity is lessening. So its kinetic energy is getting smaller. And then it reaches over here, and then it comes back around. So we have this oscillation back and forth between kinetic energy and potential energy. Now, of course, there's also energy being lost into the molecules that it's traveling through. So eventually it will come to a stop. But if you could do this in a vacuum and minimize the friction up here between the string and whatever it's hooked to, I mean, you can make it go on for many, I don't want to say months, but it would be a long time that you could make it go back and forth. Assuming you could completely get rid of all the friction, it would go on forever. So you have a pendulum here and a potential energy of 10 on the left side. So as it's moving this way, its potential energy is down to 2. What is its kinetic energy? Well, again, guys, the potential energy plus the kinetic energy for a system should always add up to the total mechanical energy. Well, what's the total mechanical energy over here? 10 plus 0, right? So the total mechanical energy is 10 joules. So right here, the mechanical energy has to add up to 10 joules. So if 2 joules for potential energy, what's got to be the kinetic energy? Well, you should see that it's 8. And then at the bottom, 0 plus what gives you 10? Well, it's 10 joules there. Right? And when it gets way back over on the other side, it's at the same height it was when it was here. And we know that its value for V stops because it gets to that max height and doesn't move. So if V is 0, that means our kinetic energy is 0. And where is all that energy gone? It's been converted over to potential energy. And the only other thing that we need to think about is why is mechanical energy not conserved? Now again, energy is conserved, but mechanical energy is not because of friction. The total energy is always conserved. That's never, ever going to change. But as you're swinging the pendulum back and forth, that mechanical energy gets lost into thermal energy, or I shouldn't say lost, it gets transferred into thermal energy, into the air molecules that it's traveling through. And that's why it does stop eventually. But if we could get rid of all the molecules and all the friction, it would go on forever. And that concludes our work and energy notes.